In the titration lab, we're going to do a lot of revamping of your lab skills. You've done a titration before in Gen Chem 1 lab, but now we're going to go back. We're going to be able to do a much more thorough analysis of it, and we're going to get into the nuance of why do we do titrations. So on the lab skills side, you have learned how to use a burette, but we're going to get really good at using it to its full precision and getting a good indicator endpoint, that one drop light pink endpoint. We're also going to learn this general technique called standardization. The idea is that when I start using a chemical, I'm probably not sure, I have its approximate idea of its concentration or its purity or something like that, and I have to kind of double check it. So we always sort of begin labs with this process. This is a very typical technique. In this case, we'll be determining the concentration of a sodium hydroxide solution, and then we'll use that value that we just found to then take that solution and do something else with it, which would be analyzing, doing another titration with tartaric acid. In terms of our learning of concepts, this is really stoichiometry review. There is understanding, a laboratory understanding of what is the difference between an equivalence point, which is a theoretical concept that we do in lecture, and endpoint, which is a lab concept. Understanding what an indicator is and a little idea about how we select indicators. And then we're going into stoichiometry, relating moles of two different reactants, and also being able to do all the conversions that are associated with it. Can you find moles from molarity and volume? Can you find molarity from moles and volume? Can you find molar mass from mass and moles? So we'll be doing a lot of those calculations in this lab. What is titration? Generically, titration is when we have a chemical of known concentration and a measured volume is reacted with a chemical of unknown concentration, or something is unknown about it. It's not always concentration. And the goal of titration is to use the stoichiometric ratio from the reaction of those two reactants to determine something about the analyte. So we basically always have two chemicals. The titrant, which is the quantity, the reactant that we know about. So like I have this known concentration and a known volume of a solution, or I have a known mass of a solution, something like that. And then we have the analyte, which is what I'm trying to learn about. I'm trying to analyze it. So that's the other reactant. So I will always be doing this. Also understanding that a lot of times we get into situations, just going to put this up there, if it's a titration, you cannot use M1V1 equals M2V2. It will work occasionally, but it will not work consistently, and it gets you in trouble because there's no coefficients in that. And the idea of relating two different reactants in their stoichiometric ratio means I need to know about their coefficients. So you can't use the dilution equation. All right, which brings us to the point. In order to get good coefficients, I have to have a balanced acid-base reaction. In Gen Chem 1, you learned about acid-base reactions. You learned how to predict the products of an acid-base reaction. You learned how to balance them. You learned how to get the net ionic equation of an acid-base reaction, of a neutralization reaction. So let's review this because you need to be able to determine, given an acid and a base, determine what the products are and balance the reaction so that you can get the coefficients. It is understood that if I just tell you the acid and the base and you know it's a neutralization, that you can write the balanced reaction. So let's go through how to do it. An acid is any substance that produces an H+ ion. Technically, then that H+ ion sticks to water and becomes hydronium ion, H3O+. But the generic formula for an acid is HA or HX. In other words, hydrogen with something else. And that's going to break apart and make H+. So we have a couple different kinds of acids. Not only do we have strong acids and weak acids, which we're not really getting into in this lab, but we have mono, di, or triprotic labs. Protic sounds like proton. H+ is a proton. So what it means is how many hydrogens does it have that will come off? There may be more hydrogens, but they're not going to be necessarily acidic hydrogens that come off. So a monoprotic acid has one H that can come off, so it will make one H+. A diprotic can produce 2 H pluses, and so its general formula is H2A or H2X. The A and the X is just kind of like a stand-in for some other chemical substance. And a triprotic acid produces 3, and so it has the general formula H3X. So I have different kinds of acids in terms of how many protons they have. And then I have bases. The job of a base is to accept the H plus and or produce hydroxide ion. So its general formula for us, for strong bases, is going to be MOH, where M is some metal with hydroxide. There aren't any special names, like monodipri, but the general formula could be 1 hydroxide or 2 hydroxides. So MOH or M parentheses OH2. And they're going to produce 1 or 2 hydroxide ions, depending. And it depends on which metal it is, right? And what the charge of that metal is determines whether it's going to have 1 or 2 hydroxide ions in it. So looking at the possible generic reactions we can have. In general, all neutralization is an acid and a base is going to neutralize, and it's going to make water and a salt. Salt meaning an ionic compound of the other things. So the way that the acid and the base make water is that the H plus from the acid and the OH minus from the base connect together to make the water. So that's where it's coming from. So it's going to depend on, I have to have an equal number of H's and OH's. So if I have a monoprotic acid, HA, and a base with just 1 hydroxide, then it's going to be a 1-to-1 reaction. So it's going to make 1 water and then a salt. If I have a diprotic acid and I have MOH, so in other words, just a base with just 1 hydroxide, then I'm going to need twice as much base. So because I need to have an equal number. So if I have 2 hydrogens, I have to have 2 hydroxides, and I will get that from having a coefficient of 2 for the base. And that's going to make 2 waters and an appropriate salt. If I have a triprotic acid, it's going to need 3 hydroxide, 3 hydrogens, so 3 hydroxides. If I'm using something like NaOH or KOH, I'm going to need 3 of them, and that will make 3 waters. Now notice that if I have a monoprotic acid with one of these bases, like calcium hydroxide, which has 2 hydroxide ions, then I'll require twice as much acid. But I can balance any 3 of these, and so you need to now know when you're given an acid and a base, how many acidic protons, is it a mono, di, or triprotic acid? And then how many hydroxides does the base have? It gets a little bit more confusing when you do weak acid, weak base stuff, but that's not going to happen until later on in the semester. The whole goal is I need the coefficients to do titration. Titration is relating something about one of them to the other one. So I need to know the coefficients. That coefficient ratio is how I compare moles of acid and moles of base. All right, so equivalence point, again, this is now a theoretical construct that we deal with in the lecture, is that every reaction, of course, requires a different ratio of reactants, and that ratio of reactants is the coefficient ratio. So the equivalence point is the point at which where I have that stoichiometric ratio. So if I'm using a diprotic acid with a base that has 1 hydroxide, and so the coefficients are 2 to 1, I need 2 bases for every 1 acid, then it'd be the point in the reaction where I have twice as much base as I do acid, and so that everything can react, and the idea is at equivalence point that all of the acid reacts with all the base and there's none left over of either one of them. Nothing's in excess. They're both the limiting reactant, we could say. And so at equivalence point, I now can make a relationship between how much acid and how much base I have. I now know that reaction from the stoichiometry. So in this case, let's say this reaction requires, I'm looking at it, it's 2 HCl's. HCl is a monoprotic acid because I see it has 1 hydrogen in it, and calcium hydroxide has 2 hydroxides in it. When I balance it, that means I need twice as much acid as base. So I need, at equivalence point, that means that if I knew how many moles of HCl I had, that I would have half that amount, that would be twice the amount of how many moles of calcium hydroxide I have. Another way of saying it is that if I knew, so I should say, let me flip it around. If I know how many moles of calcium hydroxide I have, I could double it and say, well, that's how many moles of HCl I have. Or if I knew how many moles of HCl I have, I could take half of it, and that would tell me how many moles of calcium hydroxide I have. So I just need to know one of them and these coefficients, and I can figure out the moles of the other one. That's the whole goal of stoichiometry. So let's suppose I have an unknown amount of calcium hydroxide titrated with HCl, and at equivalence point, I know that I added 18 moles of HCl. Since I know the HCl, and I know there's 2 HCl's for every 1 calcium hydroxide, I can multiply it by that ratio. So 18 moles of hydrochloric acid, again, I divide by the coefficient of the thing that I have, and I multiply by the coefficient of the thing I want to know about. So that'd be 1/2, which would mean I know that 9 moles of calcium hydroxide have reacted. So let's say I knew it was 9 moles of calcium hydroxide, and I knew its volume of the calcium hydroxide solution. I know moles, I know volume, I now know its molarity. Or let's say I know it was 9 moles of calcium hydroxide, and I know the weight of how much I reacted. I'd have mass, and I've had moles, and mass over moles is molar mass. So either way, now I can use that moles to determine something of value to me. Now, a good question is, but how would I know? Experimentally in the lab, how do I know when I've added exactly the right amount of base or acid so that there's nothing left over? And the truth is, you can't know. So we have to use some tricks, right? So what we will do is we will add the thing that I'm titrating. I'm going to add it until I know I've added just the right amount so that all of it has reacted with the thing that's in the flask, with the analyte. And one of the things we can use is an indicator. So an indicator provides a chemical reaction that changes color when there's a slight excess of titrant. So basically the idea is I'm going to be at endpoint, and that's what an indicator tells me when I'm at endpoint. Also, I could do something like use a property of the solution, like pH, something that's going to change with extra titrant added. So when I know, in other words, the idea is if I had uncapped pens in a box and I wanted to figure out how many there are in the box, one way is just to have a known amount of pen caps, and I put one pen cap, I pull out a pen and put a pen cap on until I've run out of pen caps, and then I can count how many I made. But the idea would be I'd have to know that I'm at that endpoint, and that's a trick. So we are going to use an indicator in our lab. So the indicator that we're going to use is based off of pH. Again, when I'm adding an acid to a base or a base to an acid, I know one of the properties is if it's fully neutral, it should be 7 if it's a strong acid, strong base. It's a little tricky with weak acids and weak bases. So if I react a strong acid and a strong base, when I'm at that equivalence point, the pH should be 7. So if I can find something that turns color right at about pH 7, then what I will do is I will start with an acid, so it'll be very low pH, and then I will add base, add base, add base until it's fully reacted and it's fully neutralized, but I haven't added any extra base. And at that point, I wanted to change color. So we're going to use an indicator that's going to, the equivalence point should be at pH of 7. So I'm looking for something that changes color right around pH 7. You're going to need this at the end of the semester to know that if it's a weak acid with a strong base reaction, then I won't end up at 7, it'll end up at something greater than 7. It will be in the basic range. And if it's a strong acid with a weak base, the equivalence point is going to be lower than 7. You'll learn that skill in the very end of the course, is how do we predict the pH at equivalence point if it's not strong acids and strong bases. All right, so then again, the endpoint is when the indicator changes color. And it's not identical to the equivalence point. And in fact, the way it works is usually I've had to add a little bit extra titrant. So I'm actually a little bit past the equivalence point, but hopefully just by a tiny bit so that it's close enough consistently that I can get a good value. And so we're looking for, remember, something that turns, we're going to use a strong acid and a strong base. So we're looking for something that turns color at about pH 7. And the one that we typically use is something called phenolphthalein. And phenolphthalein changes color at pH 8.2. And I know you're saying, well, 7 and 8.2 are quite far apart. It turns out in pH scale, they're actually only off by about a drop of a weak concentration base. So they're pretty close, and that's the one we're going to use. There are other indicators that we would use if we had some of those weak acids, strong base, strong acids, or strong base, weak acid, where I need it to change color at a different pH. And that gets into more complicated chemistry that we're not going to be doing in this course. So we're going to use phenolphthalein, and it's going to turn, it's clear at pHs below 8.2, and it turns pink, bright pink, at right around pH 8.2, and it stays pink and gets even darker pink as you go to higher and higher pHs. Okay, so you've done a titration before. You remember that it's really complicated because, again, I'm going to add in, I start with acid in my flask, I'm going to put base in the burette, and it could be flipped, it doesn't matter which one. And I'm going to add from the burette drop by drop, and I want to get to a point where with one drop it changes from clear to pink because we're using the phenolphthalein indicator. And that is really impatient because you're going drop by drop for like tons of milliliters. It's about 20 drops in a milliliter, so you've got, it's probably even more, it's probably more like 40 on our burettes. So it's just too much time. So you're going to get impatient, and then you get impatient, and then instead of adding one drop, you add a bunch of drops, and then it goes from clear to dark pink. So you need to be patient. So two things that we can do. One is a throwaway trial. In a throwaway trial, I say, like, I just want to get ballpark volume of how much titrant I have to add. So you measure out your analyte into a flask, and then you add the titrant like 1 milliliter at a time. 1 milliliter, 2 milliliters, 3 milliliters total, 4 milliliters. So you're just adding it like 1 milliliter at a time instead of a drop by drop. And then it'll go from clear to dark pink. But that gives me an idea, okay, you know, if I added 10 and it was clear, and then I added another milliliter and now I have 11 milliliters and it's dark pink, then I know that the endpoint is somewhere between 10 and 11 milliliters, which gives me, on the second time, I could use that. Now, if you do a throwaway trial, it is incredibly inaccurate. So you don't even count that as a trial. It's really just I'm just using some stuff and getting a ballpark number. You might write the numbers in your lab notebook, but it's not a trial. Do not use a throwaway trial, a throwaway run as a trial. The other thing I can do is use a little bit more math. So I can get closer than just between 10 and 11 by if I know approximately the concentration of my analyte or something about my analyte. So let's say I know it's approximately 0.2 molar. I can use the weakest possible concentration to find an estimated volume. So in other words, I assume, okay, well, let's assume it is 0.2 or 0.18 molar or whatever it is. I'm going to find the minimum amount of moles I would need to react what I have in the flask. So I'll know a volume of what I'm going to use and an approximate molarity. Volume and molarity gets me moles. And from that, I can determine the minimum amount of moles I might need to add. And then I multiply that by a coefficient ratio to determine how many minimum moles I would need of titrant. And then I would take the volume of the titrant, is the moles of the titrant that I need, divided by the molarity of my titrant. And then it's covered over by my face. But so let's say I do a calculation and I say, if this is I use 25 milliliters of sodium hydroxide, and it's approximately 0.1 molar, then that means I'm going to need 0.025 moles of sodium hydroxide. And since if I'm going to react it with HCl, and that's a coefficient of 1 and 1, that would mean I need 0.0025 moles of HCl. And let's say I'm using 0.1 molar of that, then it would turn out, oh, I'm going to need 25 milliliters of the HCl. So if I think that I've calculated that it's going to take 25 milliliters of HCl, I would want to take about 80% of that. So I'd say, all right, whatever, 8.8 times 25. So maybe it's like 22. And I would just start and add 22 milliliters of HCl into there. And then I'd start going drop by drop. And again, it doesn't matter whether it's HCl or NaOH. The idea is that I know the amount of one, and I figure out for the other one how much I would need. And so now, regardless of which is the one that I'm adding drop by drop, I can add most of it right away on the first time I open up the burette, and then go drop by drop. And that's going to be much less work for me. So I'm going to have you do this. I'm going to give you in the Prelab the approximate concentration of the sodium hydroxide that we're going to standardize, and the approximate volume of the acid and the molarity of the acid, and you'll have enough information to determine the approximate volume of NaOH that we're going to need in our titration. Please write that down in your notebook, because I'm going to check it when you get to class. We're going to need that in the lab during the experiment. So I want you to have that calculation written out in your notebook. All right, what are we doing basically? Part A, we're going to titrate 25 milliliter portions of known concentration HCl. It should be about 0.1 molar, but sometimes it changes, so we don't know the number until you see it on the bottle in the lab, but we do know it. And then we're going to titrate that with NaOH, and I don't know the concentration of the NaOH, but it's somewhere between 0.18 and 0.22 molarity. So I want to find the molarity of the NaOH. This process is called standardizing, because we're going to use that molarity of NaOH in a later step. All right, then the next task is I want to weigh out a very small size sample of tartaric acid, something that's like only 0.0, like 1 or like 7 milligrams, so it's like 0.007. I'm not going to get an accurate measurement of that on the scale. I think actually the number we need is 0.020, so 20 milligrams. It's a small sample. I'm not going to be able to weigh that out very precisely because my scales only go 3 decimal places. So what I will do is I'm going to say, well, let me weigh out 5 times that amount and dissolve it in water to a certain known amount, known volume, and then I'm going to take just a portion of that. So if I were to take 1 gram, weigh it out, and I put it into 100 milliliters, and then I just take 20 milliliters of that, I've taken 20 over 100, or 1/5 of what I weighed out. So I really only have 1/5 of a gram. So now I'm able to precisely measure out a very small mass. This is a known technique that we call, using aliquots of solution. And so we're going to do that. But the problem is, when I go to do my calculations, I can't use what I actually weighed out. I have to remember, but I proportioned it by only taking some of it after I diluted it. So you're going to weigh out a mass of tartaric acid, dissolve it into 100 milliliters, and it has to be precise, so we got to use a volumetric flask. And then I'm going to precisely take out 20 or 25 milliliters. I can't remember which one it is, using a volumetric pipette. And then I will really only be having a proportion of that, what I weighed out in there. All right, then once I've done that, now I'm going to do titrations of 25 milliliters of that prepared solution of tartaric acid with that same NaOH, but now I know the molarity of the NaOH. So I know the volume of I know the mass of what I have in the flask, and I know the molarity of the NaOH when it reaches endpoint. Then I also know the volume, so now I can figure out moles of NaOH, relate it to the moles of the tartaric acid, which is a diprotic acid. So I'll have to use my coefficients to figure out how many moles of diprotic acid I have, and I know its mass and I know its moles, so then I can find its molar mass. Of course, in each part, we're going to be doing multiple trials. So when you weigh out the second step, you're just going to make 1 solution. That's enough for 4 trials. Well, it's really enough for 3 trials, but if you need to make more, we can make more. But we're going to do at least 3 trials in part A and at least 3 trials in part B. And then we're also going to do some statistical analysis of them in the write-up. All right, so more specifically, part A, the standardizing of NaOH. You're going to have to come in, record the molarity of the HCl from its bottle. Again, it should be about 0.1, but record whatever the bottle says. We need that information, so make sure and you write it down. And then we're going to prepare 2 burettes, one for my acid, my HCl solution that's in a bottle, and one for my NaOH, also provided to you in a bottle. However, the NaOH, we're not really sure of its molarity. When we prepare a burette, remember we have to condition it with the solution we're going to put in it. So you have to empty it, then rinse it 2 to 3 times with that solution that we're putting in it. So you're going to do one for the acid for the HCl and one for the base. And you're going to have to label the burettes with what's in there. It's important that we don't confuse the acid and the base. Then you're going to use the burette and add approximately accurately 25 milliliters. Just a reminder, approximately accurately means it can be approximately 25 milliliters, but I better know it accurately. So don't tell me 25, tell me 24.97 or 25.02. So whatever it is, we make sure you're recording it. Make sure you know you have to record your initial and final burette volumes. And then you're going to open up, put the acid solution from the burette into a flask. Again, to get 25 milliliters, I read my initial burette reading, and I add the number 25 to that. That will tell me about where to stop to have added 25 milliliters. And then I precisely read the final burette reading. And then you're going to have to add in a little bit of water. It's very ballpark. It just helps to have a little bit more volume to swirl it to make sure everything's reacting and mixing well. So somewhere between 50 and 20 milliliters. You can just eyeball it from the markings on the flask, or you can use a graduated cylinder, but it's not precise. And then you're going to add 2 to 3 drops of that phenolphthalein indicator. If you don't do this, it will never change color. So it's important to make sure you do that. And then you're going to start adding the NaOH from its burette, taking the initial burette reading first, until 1 drop of it turns it a light pink. And then that color has to remain for 30 seconds. So when you're getting close to that point, again, we've talked about how you add an initial amount of a certain percent so that you could get closer to it. But when you get close to that point, and you can tell by the fact that you've calculated or the fact that it's taking longer, it will turn pink but then go back to clear. And it takes longer to go back to clear. That's telling you you're getting closer and closer to your endpoint. So when you get to that point, you want to wash down the flasks with water because you don't want NaOH to be sitting on the side of the flask and then all of a sudden a lot of it drops into your flask. And then you're going to, if you happen to overshoot it, in this case, because we still can add just like 1 more drop of acid from the acid burette, we can back titrate. So you can now go back to your acid, add another drop, it'll turn back clear again. If it maybe turns light pink, if it turns clear again, then you go back and add another drop of base. So you're going to do that 3 times or until you have 3 good titrations. If you ruin a titration trial, then you may have to do it 4 times. You need 3 good titration endpoints. Again, don't forget, every time we use a burette, we take 2 readings of it, and they should always be to 2 decimal places. The finding molar mass of tartaric acid. So this is the second titration. It's pretty similar. It's still a titration, but we're going to do a couple things different. Again, remember, first we're going to make that solution. We're going to weigh out approximately accurately 1 gram of tartaric acid, dissolve it into distilled water to make 100 milliliters of solution using a volumetric flask. And then we're going to take a precise measurement like a volumetric pipette and pipette out just 20 or 25 milliliters. I can't remember which one the instructions say. I think it's 25 milliliters. So we're going to make sure you've topped off the sodium hydroxide burette, so you're ready, take an initial reading. Then in your flask, rather than putting in acid from a burette, you're going to use a pipette and take 25 milliliters of that solution you made of the tartaric acid. And then still add 15 milliliters distilled water. Again, it's approximate. Add 2 to 3 drops of phenolphthalein and repeat the process, now adding NaOH to it until it turns light pink. This one's harder to do because there's no way we can do a prediction on it. We can't make any estimates. You can do a throwaway trial if you want. However, know that you're probably not going to get with precision all for 25 milliliter portions out of that 100 milliliters. You really, by the time you take the pipette out, the first, the second, the third, the fourth one, usually it's a little bit short. You can't get all the way out. So you really only have enough for 3 titrations. Not a problem. You can either go a little bit light on the first one or just make a second batch of solutions. Okay, anyways, you get the endpoint. Again, light pink. There is no back titration here because, again, we added from a solution that we made, so you can't like just add another drop and have it quantitative. You would have to, so you're just gonna have to start another trial. So that's a little bit trickier, but by this time you've just done a bunch of titrations, so hopefully you can figure that one out. Again, always take your initial and final burette reading. When we finish, all the waste goes in a waste carboy. Make sure that you empty out your burettes, and that will go to waste. All of your titrated mixtures, pretty much everything. The remaining acid and base from your burette. If you had a beaker with extra acid or base that you're going to use to top off the burettes with, that goes in the waste. Pretty much everything is going to go in the waste. You can just kind of pour it all into one beaker from all your containers, dump it in the waste, wash out all your glassware, leave it drying. After you rinse the burette with water, then make sure you fill it with distilled water. You want to leave it filled with water so that dust can't stick on the insides. I'll see you in lab. One more thing. We are going to need to do standardized data on the Part A titrations. So at the end of your lab, I need to have the results, the volume of HCl and the volume of NaOH for your first 3 trials that you use for Part A. I don't need the Part B with the tartaric acid. So make sure you don't leave without that, because I will take off on your lab report if you leave lab without giving me this data, because I need to have the whole class's data to give out to the whole class. So in a non-identifiable way. So I need to have that before you leave lab. All right, I'll see you in lab.